Hey, my most excellent rock buds, it's Rock Papa. I hope you guys are doing fantastic wherever you are in the world. Today we're going to talk about the rocks and geology of the Grand Canyon, a most spectacular place. We'll look at the rock layers that line this famous canyon, and we'll find out what each one is made of. We'll look into how they're formed. That will involve a little bit about a very ancient island arc crashing into a very small continent. We'll talk about transgressions of the sea that happened. We'll look at the most ancient rocks at the bottom of the Grand Canyon and the great unconformity on the top of these rocks. We'll look at the layers that demonstrate the cyclotherms that happened during the Allegheny and orogeny as the glaciers melted and reformed. And finally, we'll take a look at some of the great sand dune eras, some of the greatest sand dunes in the world. So stay tuned. I hope this will be interesting to you. If so, please subscribe. And so many thanks to my most excellent subscribers. I appreciate every one of you. So here we go. The geology of the Grand Canyon. As you guys likely know, the Grand Canyon is part of Grand Canyon National Park, and it's located in the northwestern part of the state of Arizona. The mighty Colorado River has cut down through the rock layers, creating the Grand Canyon over a period of at least 5 million years, according to geologists. It has created a north rim and a south rim, each of which provides spectacular views of these interesting rock layers. Let's begin our investigation with a Grand Canyon slideshow. Okay, so this very excellent drawing shows the three main rock categories that we find in the Grand Canyon. Let's take a look at them. Down at the very bottom of the Grand Canyon along the Colorado River, we have the very oldest rocks, and they're called the Vishnu Basement Rocks. And these rocks range in age from 1.8 billion to 1.4 billion years ago. We'll take a closer look at these rocks in a little bit. Above the Vishnu Basement Rocks, we have the Grand Canyon Supergroup Rocks. These rocks are about 1.25 billion years old to about 650 million years ago. And by the way, capital M little a stands for million years ago. It's actually mega annum, which is a Latin term. The Grand Canyon Supergroup rocks are missing in lots of areas of the Grand Canyon because they were eroded away in those sections, but you can see them in the eastern Grand Canyon area. And finally, on top of everything is the stack of Paleozoic rocks that are between 550 million years old to 250 million years old. These rocks record the geologic history of the area right after the supercontinent Rodinia rifted apart. Hey guys, so now we'll take a closer look at each one of these rock categories and get into them in some detail. Okay, spotlight Vishnu Basement Rocks at the very bottom of the Grand Canyon. Here's what they look like from afar. They're kind of very dark brown or black rocks. But down at the bottom along the Colorado River, they can look pretty colorful. This stuff is the Vishnu schist found right down along the Colorado River. Pretty stuff. These Vishnu basement rocks are very ancient. They began forming about 1.8 billion years ago, when subduction caused an ancient volcanic island arc to crash into a small continent. As the supercontinent Columbia was forming, Columbia was right before Rodinia. Here's what that probably looked like. The bottom edge of the ancient North American continent, pretty small at that time, was about where the southern part of Wyoming is now. And that island arc that is crashing into it would become the Vishnu basement rocks. As this terrain was added to the continent, as we know, subduction creates and enlarges continents. Before we describe these rocks, let's just have a quick peek at what some of them look like. Here's a list of the Vishnu basement rocks. The oldest rocks are on the bottom of this list, the youngest on the top. First we have the Brahma schist. Sounds like something that comes out of a cow in India, doesn't it? The Brahma schist is most likely basalt lava, which was part of ocean crust that was pushed up onto the continent as the island arc crashed, then later metamorphosed into schist. Next we have the Rama schist, which is metamorphosed rhyolite lava produced probably as the volcanic island chain began to form and fractional melting happened. Hey guys, you likely remember that when volcanic island chains form by subduction, the subducted ocean crust, which is mostly mafic basalt lava, brings down a bunch of water with it, and that causes the basalt to break up into felsic, intermediate, and mafic magmas and lavas, and that's called fractional melting. And that's very likely where the rhyolite lava came from in the Rama schist. Next we have the Vishnu schist, which is very likely to be sand and mud that was washed off not only the edge of the continent but also the volcanic island chain as it eroded into the foreland basin it formed as Columbia's supercontinent was coming together. I believe that the Zoroaster metadiorite and the older granite rocks were emplaced as island arcs crashed into the continent. And finally we have the younger granites, which were intruded into the older granites, indicating that some tectonic activity was taking place, possibly the breakup of supercontinent Columbia, or the very early stages of the formation of supercontinent Rodinia. Hey rock buds, a couple of things about the Vishnu basement rocks. First of all, how come these two granites that we talked about, the older granite and the younger granite, remained granite and didn't become metamorphosed rocks? I think it's because that area of the continent became the core of the North American continent, or craton, and the subsequent tectonic activities were far enough away from it to emplace granite, but as the supercontinent Rodinia grew larger and larger, the crashing events, which always occur at the edges of the continent, were not able to fold and fault these granites and turn them into granite gneiss. Another thing is that the source of the Vishnu basement rocks, as I've explained it, is pretty much accurate, but geologists don't know 100% how they formed. But logically speaking, if you look at the way that continents form today with island arcs, subduction island arcs, and crashing, it makes sense that they are the way that I've explained them. Before we leave the Vishnu basement rocks, it's important to talk about the great unconformity. What is an unconformity? It is a place in the layers of rocks that record geologic time where a whole bunch of those rocks are missing. And this picture shows what Grand Canyon geologists call the great unconformity. And that's that little white line that goes horizontally across the picture. Below that is the Vishnu basement rocks. And we've got about 1 billion years of missing rock layers between the two. This means that most of the rocks that represent the coming together of Rodinia supercontinent and its subsequent rifting are missing. More than likely, these rocks were deposited and then later eroded away, because we have in places in the Grand Canyon supergroup, which do represent the forming and rifting of Rodinia. So let's take a look at the Grand Canyon supergroup rocks next. And since we're talking about unconformities, this picture shows the unconformity that lies between the Grand Canyon supergroup of rocks, which are they're tilted red rocks there. That's how you can spot them. They're tilted layered rocks that are red, and the Paleozoic rocks above them. The number of missing rock layers varies with this unconformity, but goes up to about 750 million years of missing rock layers at the max. The Grand Canyon supergroup has two main subgroups. The oldest one is the Unkar group, deposited between 1.255 billion years ago and 1.08 billion years ago. The Unkar group of rocks represent sediments that were deposited in a four-land basin as supercontinent Rodinia came together. We're talking about dolomite, which originally was limestone that was deposited in the shallow and clear parts of the foreland basin, and then the muds that became shales that first came off the eroding mountains, followed by the sands that came down as the mountains eroded in earnest, created a coastal plain and beach areas that overwhelmed all the other sediments and completed the filling of the foreland basin. Then came basalt lava flows associated with more subduction as Rodinia continued to come together. Hey, rock buds, the Unkar group of the Grand Canyon supergroup rocks, which is on the bottom of that group, has metamorphic rocks in it like the quartzite. But the next group, the Chuar group that we're going to see, which is on top of the Unkar group, has only sedimentary rocks. The Chuar group shows us that Rodinia was rifting apart, and the sediments represented by the Chuar group rocks were deposited in Rodinia rift basins. And 80% of this material was muds that were super rich in organic matter and very rich in fossils. So what in the world was going on in these Rodinia rift basins? Well, plate tectonics had moved Rodinia up into warmer climates by this time, and this stimulated the tremendous explosion of blue-green algae in the ocean that created a lot of organic matter. Here's a modern-day example of what those algae mats would have looked like, and their presence stimulated a huge growth of single-celled organisms. All this resulted in huge amounts of organic material in these muds. And here are some of the fossilized remains of those algae blobs, and we call them stromatolites. Hi, Rock Buzz. So now is probably a good time to do a quick and dirty summary of what we've talked about so far, so let's do that. At the very bottom of the Grand Canyon, you have those dark brown to black Vishnu basement rocks right along the Colorado River. and they are rocks that are associated with the coming together and likely rifting apart of supercontinent Columbia, and that happened between about 1.8 billion years ago and about 1.4 billion years ago. And then above the Vishnu Basement rocks, we have the Grand Canyon supergroup of rocks. These are layered rocks that are reddish and tilted, and they are not present throughout the Grand Canyon, but are more evident in the eastern part of the Grand Canyon. Between these rocks and the Vishnu Basement rocks below, there's an unconformity which represents rock layers that are missing. And then we're getting ready to talk about the last stack of rocks, the Paleozoic rocks, which were deposited after Rodinia rifted apart. And there's another pile of missing rocks, another unconformity between these Paleozoic rocks and the Grand Canyon supergroup of rocks, and between the Paleozoic rocks and the Vishnu Basement rocks. So let's move on to the Paleozoic rocks, the main event of the Grand Canyon. Okay, now let's look at the big stack of rocks on top of everything. These are called the Paleozoic rocks, and they were deposited between 550 million years ago, which was the beginning of the Cambrian period, and about 250 million years ago, which was the end of the Permian and the beginning of the Triassic period. After Rodinia supercontinent rifted apart, all the resulting continent pieces, including ancient North America, began to sink. This always happens after a rifting event, and if you look at the video that I did on isostasy, you can find out why. A sinking continent means the sea is rising, and geologists call a rising sea a transgression. And this transgression creates a very specific set of sediments called the rift-to-drift sets. First, you have the sandy coastal plain and the beaches on the edge of the continent. And as the sea rises up, it brings mud from the intercoastal waterways up on top to cover the sand. And as it even continues to rise, the limey mud that's further out comes up and covers the intercoastal waterway mud. After this transgression of the sea is over, you have a very widespread layer of sand that turns into sandstone, covered by a very wide layer of mud that turns into shale, and that's covered by a very widespread layer of limey mud that becomes limestone. And these layers taken together are called the rift-to-drift sequence of sediments. The rift-to-drift sequence of sediments covered just about the entire North American continent. And in the Grand Canyon, they lay right on top of the Vishnu Basement rocks or right on top of the Grand Canyon supergroup rocks. And they're called the Tapeats sandstone. And on top of that, you have the pretty extensive Bright Angel shale, which is kind of greenish. And on top of that, you have the thin layer of mauve limestone. You know, I just said they were laid down on the Vishnu Basement rocks and the Grand Canyon supergroup rocks. Yes, but there are huge amounts of sediments representing huge amounts of time missing in between the rift-to-drift and what's below it. That would be those unconformities that we talked about earlier. Here's a nice graphical representation of the rift-to-drift sequence. And the rift-to-drift sequence was laid down during the Cambrian period between 550 million years ago and about 500 million years ago. Hey, rock buds, interestingly enough, there are no rocks present in the Grand Canyon representing the time periods from Ordovician, which began about 500 million years ago, and through the end of Devonian, which ended about 350 million years ago. Now, what's going on with this? It's likely that these Ordovician through Devonian rocks were laid down but eroded later, and I can think of two reasons why this might have happened. First of all, during that period we had some major glaciation, And what does glaciation do? It sucks up the seawater, lowers the sea, exposes the land to weathering and erosion. So it may have been eroded during that time. Also during this time, we had the Taconian orogeny, which, as you guys may remember, creates a foreland basin and a forebulge where the land is flexed up above sea level and erosion can occur. And this forebulge, as well as the foreland basin, migrated all the way across the continent. So I think these two factors probably raised the land up so that whatever sediments were laid down were eroded away. Next, during the Mississippian period, which lasted from about 350 million years ago to about 330 million years ago, we had the Red Wall limestone. This tells us that the Grand Canyon area was covered by a shallow, warm sea where limestone could be produced. And once again, just about the whole North American continent was also covered in this warm, shallow sea, and a layer of limestone, which includes the Red Wall limestone, was laid down all across the continent. Once again, what is going on? Hey guys, my best guess as to why virtually the whole North American continent was once again covered by shallow, warm seas is the Alleghenian and Wichita orogenies. In other words, Africa was crashing into the North American continent in the Alleghenian orogeny. As you know, that produces a massive foreland basin. It pushes down on the crust, creating a foreland basin, and that foreland basin once again migrates across the continent. That's the best reason that I can think of for this huge inundation of the shallow warm sea that produced all this limestone. Here's some nice pictures of the Mississippian period Red Wall limestone for us to look at. During the Pennsylvanian time period from about 330 million years ago to about 300 million years ago, the Grand Canyon received a sequence of sediments that are called the Supai group. Let's look at some pictures while I talk about what was happening. On the west coast of ancient North America, you had the Antler orogeny mountains, which were contributing sediments into this area, and on the eastern side, you had the Alleghenian orogeny mountains, which were contributing sediments from the east. These sediments were mostly muds that turned into shales, intermixed with some sand layers that became sandstone. When you look at Supai group rocks, you can see a lot of horizontal lines in them, and this means that the sediment layers changed over and over and in repeating sequences. And this was because the glaciers during this period were coming and going many times. And they call this glaciers coming and going. They call it cyclotherms. During the Permian period, which lasted from about 300 million years ago to about 250 million years ago, the supercontinent Pangaea had been completely assembled, and the Grand Canyon area had migrated up into the hot, dry northeast trade wind belt just above the equator. These strong, consistent northeast winds associated with the dry climate picked up sand and began to pile it into sand dunes blown toward the west and southwest, creating the first of the great sand dune deserts that would come to dominate the area in the future. This first layer of sand dunes became the Esplanade sandstone in the Grand Canyon, and also the very picturesque Cedar Mesa sandstone of Canyonlands National Park Needle section, where Grammy and I have spent many a day frolicking among these beautiful rocks. The Hermit Shale, which is above the Esplanade sandstone, represents probably a little bit moisture time when rivers overflowed the sand, depositing these river-borne muds that became the Hermit Shale. Probably there was some river conglomerate in there too. And then drier conditions prevailed again, and we got the sand dunes that would become the very picturesque Coconino sandstone layer. Coconino sandstone is one of the two lighter layers that you see near the very top of the Grand Canyon. During late Permian time, the sea began to rise again in a marine transgression. The first transgressive pulse of the ocean created the Toroweap Formation, which created thin deposits of gypsum, mud, and sand at the edge of the sea. And then came a major sea transgression that covered most of the Colorado Plateau, which consists of the states of Utah, Colorado, Arizona, and New Mexico. This transgression spread a layer of limey mud across the area that became the Kaibab Limestone. Kaibab Limestone tops off the Grand Canyon, and when you're walking along the edge of the Grand Canyon, north or south rim, looking at this beautiful canyon, you're walking on the Kaibab Limestone. Okay, rock buds, that's it for the Grand Canyon rocks. Thank you so much for watching and for hanging in there with me. I know it was a long video. Hope this was informative. If so, please subscribe. And this is your Rock Papa saying, happy rock hunting to all my fantastic rock buds. Papa out.